Hello, today we are going to do section 1.2, and section 1.2 deals with quantitative data and making graphs with quantitative data and describing the graphs. So quantitative data is like this. It's basically a list of numbers in essence, whereas categorical data, like we talked about last section, the numbers are counts and categories. So it's very important that you're able to make that distinction. But in general, when you see a list of numbers like this, you're saying this is quantitative data. And the goals for this section, you really need to be able to do 5 things. You got to be able to make a dot plot, and that's real easy to do. It's just a number line with dots above it. You got to be able to make a histogram, and that's a little more complicated, but we'll discuss it shortly. And then you got to be able to make a stem plot, otherwise known as a stem and leaf plot. You may have done that earlier in your career. Then we have to describe distribution, all right? Describe, which is just a list of numbers. So we have to be able to look at a graph and describe it. And when you're ever asked to describe it, you do what is you cuss. And so what that means is the C stands for the center. You must discuss what the center of the numbers are. You just kind of look in the center and you say, well, these numbers are centered around whatever it is. And you sort of make a guess. Now in the next section in 1.3, we're going to calculate numbers that describe the center, namely the mean and the median for the most part. All right. So, but for now, we're just going to eyeball it and say it looks to be centered around whatever it's centered around. The U stands for unusual values. So more commonly called outliers. In other words, are there points that really stick out from the other points, that are outside the pattern of the other points? And for right now, we're just going to make a subjective judgment in that regard. But we'll have a formula for that the next section, and we'll be more exact about it. But for now, we'll just look and see if there's any really unusual points outside the pattern of the other points. And then the first S is the shape. And we'll talk about the shape. Is it mound-shaped? Is it bimodal? Is it symmetric? And I will give you some terms that you need to say in order to describe the shape. And then lastly, you have to describe the spread. All right, and how spread out the numbers are there. In the next section, we'll have specific statistics, specific numbers that describe the spread, such as the standard deviation, interquartile range, and range. But for right now, you can just say the numbers vary from the smallest number to the biggest and just say what they are. So that is what is known as cussing, and that's really the center of this chapter. That's is being able to cuss properly. That's really sort of the main focus or the most important thing in this chapter. And then lastly, if you're given 2 distributions, if you're given 2 listed numbers, to be able to compare them. And the way you're going to compare them is by cussing on both of them and using comparative phrases. And so we'll look at an example of that. So that's what I want you to try to make sure that you can do in regards to section 1.2. And so here's your little note sheet. So let's take good notes, and please contact me with any questions you have about any of this. And so this one says the time that it takes workers at a factory to assemble a part to a boat motor on a particular day is shown below in minutes. Create a dot plot of this data, create a histogram of the data, and also create a relative frequency histogram with the data. So it's asked us to do 3 things. So first of all, a dot plot. And so all a dot plot is this. And if you can't remember how to do any of the graphs, frequently in the world of stats, it'll give you a list of numbers and it'll say draw a graph. And people will forget how to do, a histogram or a stem plot or a box plot, which we're doing in the next section. The easiest thing to do is just make a dot plot. So all you got to do is draw a number line. And, the numbers are varying from 12 to 32. Now, a lot of times when you're drawing the scaling here, you can do a scaling at the beginning that doesn't work out very well, and so you have to start over, and that's fine. I'll go in like units of 2, let's say. So if we go 12, and then to 14, and then to 16, and then to 18, 20, and so forth, 22, 24, 26, 28, 30, 32, 34. And that is what is known as scaling. It's always, here's an important law, always label and scale, always label and scale your axes. That is common error. A lot of times people on the AP Stats exam, they will do a beautiful job of drawing a graph and they'll leave out just a label or scaling, and they only get partial credit, and that's kind of sad. But you just have to draw scaling. You technically only have to draw 2 numbers. Now, this graph doesn't have to be the neatest thing in the world, but we just want to, in general, see what's happening with the data. So that's the scaling. The labeling is to say the context. So this is assembly times for a boat part. So we can say assembly times So we can say assembly times, and always put the units if there is one, and this is in minutes. So there we go. So that's labeled and scaled. And so now I just put dots above it. Don't put dots on the line, by the way. Put it above it. So 12.1. So 12.1 is about right there, and 12.3 is like right there, and 14.2 is like right there, and then 14.9 I'm going to say is there, and then 15.0 is about there, and 15.9 is about there. And then we have 16.1, 16.5, 16.7, 16.8 occurs twice. So I'll do that, put one on top of the other. And then 16.9, 17, they kind of get bunched up there. That's okay. I mean, that's sort of telling us there's a cluster of numbers there, as we're going to say. And then, so 18.3, so that's about there, 18.4, 19.1, 22.4, and 24.9, and 26.7, 29.3, so 29.3, and then 32.7, and that's it. That's all there is to drawing a dot plot. So, and so there you go. So we appear to have kind of a cluster of values here, and they're more spread out over there. And so now, so the next thing it wants us to do to create a histogram. Now, creating a histogram is a little bit more complicated. And by the way, your calculator, you need to get a graphing calculator, a TI-84 really. And if you can't get one, you need to talk to me about it, but you really need one for yourself. It's going to be able to make a histogram for you. So your calculator is going to be able to do this, but you do need to understand what your calculator is doing. So, you know, for the first couple, I'm going to ask you to do these by hand. So to make what is known as a histogram, it looks like a bar graph, but it's technically not a bar graph. So to make a histogram, this is what we're going to do. We are going to make, first of all, we have to make what is known as a frequency table. So a frequency table, and we've got to come up with intervals, or what we like to call classes, to make a frequency table. And so what we'll do is we'll look at our data. Our data is varying from 12 to 32.7. So I'm going to create intervals for the data. You want, and you can create different size intervals. That's kind of up to you. But in general, you want to have certainly at least 4 or 5 classes. And you can try it, you know, with one class size. So the numbers start with 12.1. So my first class, I'll just start with 12, and I'll have it go up 4, so it'll be 12 to 16. So that would be my first class of numbers. And then the next one would be 16, and that class size have to be the exact same every time. So I'll go 16 to 20. All right, and then the next one's 20 to 24. And then the next one will be 24 to 28, and then 28 to 32. And then 32 to 36. So there's my, you could have gone maybe a class size of 3 or class size of 5. You have some liberty here. So those are class sizes. And then we are going to go with frequencies. And you could make tally marks or, you know, but I'm going to just count up 12.1, the number between 12 and 16. Well, that's going to be 1, 2, 3, 4, 5, 6. So there's 6 of them. Now, by the way, so that's the frequency, or the number of numbers that are between 12 and 16. And these classes are inclusive on the left side. In other words, if 16 would go into, if it was exactly 16, it would go into this class. It's inclusive on the left side. And so this represents every number from 16 to every number below 20, okay, like that. And so this one is every number greater than or equal to 20, but less than 24. And if you think about it, it has to be inclusive on the left side, because 12 has to go in this class, okay? There's no class above it. So anyway, and so 28 would go in this class right here. Well, anyway, so let's count up the numbers between 16 and 20. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 of those. And then between 20 and 24, we just have 1. Between 24 and 28 is just 1. Between 28 and 32 is just 1. And then that's just 1. And so that's what we call a frequency table. Now, all a histogram is going to do is we're going to make bars. We're going to go like this. And every histogram, so this is going to be your histogram, your frequency is the labeling of your vertical axis, of your y-axis. And in this case, the biggest number is 10, so I'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I put 10, and I put 1. So because I put 2 numbers down, I would get credit for scaling the y-axis, and I've labeled that as frequency, so I get credit for labeling. Then you just put your classes on the horizontal axis. So you would just go 12, 16, and so forth. 20, 24, 28, and 32, and 36. And so, and you have to label this, and once then this is assembly time for a boat motor. So assembly times, and put the units and minutes. Once again, please do not forget to label and scale your axes. And then we just put bars up to the frequency. So between 12 and 16, there's 6 numbers. So I go up to, let's see, 3, 5, 7, 9. So 6 is right there, so I go up to 6, like that. And so then I go up to 10. For between 16 and 20, I go up to 10. And so then, and then the rest of them are 1. Okay? Now, it's important. Do not leave gaps unless there's 0 in a class. Okay? If there was 0 in a class, there would be a gap of numbers. But don't leave gaps between the bars of a histogram. Like a lot of times you'll see that in a bar graph. So this is not a bar graph. A bar graph is with categorical data like we did in section 1. Like if we were doing, people's race or what state they were born in or their political party affiliation, some categorical variable, something that categorized them, in which case most of the time we'd leave a gap between the bars. A histogram has no gaps unless there is 0 in a class. So that is that, and that's how you do a histogram right there. That's how you do it. And lastly, before we describe it, what is a relative frequency histogram? Relative frequency just means as opposed to frequencies, we're going to put percent of values. It'll actually look exactly the same. And so relative frequency, we would say, okay, we need our total number of numbers. And so we have 16, 17, 18, 19, 20. So our n, in essence, our n is the notation for our sample size. Our n is 20. And so relative frequency, and I didn't leave myself a lot of room here. So this is frequency. And so relative frequency is the proportion that are in a class. Not the number, but the proportion or the fraction. And so the relative frequency for 12 to 16 would be 6 out of 20. Okay, you just divide everything by 20, so that's 0.3 or 30%, 0.3. Like that. And so then this would be 10 out of 20, 10 out of 20, so 0.5. So half of the numbers, relative frequency tells you the percent in essence that are in each class. So 0.5 or half the numbers are between 16 and 20. And then the rest of these are 1 out of 10, which is 0.1. So relative frequency just means make proportions out of them. Just divide by your number of numbers. And then the histogram will look exactly the same. It'll look exactly the same, except for it's in proportion now. So we would call this relative frequency. And it would be our biggest relative frequency. So, and we would just say, well, it's, to make it look exactly the same in regards to our scaling, it's going up to 0.5. So if I go 0.1, 0.2, 0.3, 0.4, 0.5, so 0.1, 0.2, 0.3, 0.4, 0.5. I just went up to 0.5 because that's my biggest of my relative frequencies. And then if we went, once again, 12 and 16, and 20 and 24, and 28, and 32, and 36. And so between 12, so this would go up to 0.3, so 0.3 is like that. And then the next one's 0.5. And the rest of them are 0.1. So it would actually look exactly the same. And in essence, you could just change the scaling on your histogram. So that's relative frequency. So you can look at a relative and you can see the percent that are in each class. So so there we go. Now, sort of the heart of the section is we have to be able to cuss. And so we have to be able to describe the above distribution by cussing. In other words, stating what we believe its center, does it have any unusual values, what is its shape, and what of its spread, and does it have any clusters or gaps? Clusters is just a buildup of a large number of points, such as this would be a cluster of points there. And are there any really noticeable gaps? You would need to state those as well. And so when you look at this and you're going to cuss, and you have to write out a few sentences here, and you have to state it in context. So we would say, the center of this is really around 20 to 24. We'll come up with more scientific numbers about that next section. So we'll say that. There appear to be no outliers, I don't think. And so we would say there doesn't really appear to be any outliers. In other words, ones that are really way off, and we'll come up with a formula for that next section that'll make that a little bit more scientific. The shape, this is what we're going to call right skewed. All right, and the shape is the most ambiguous part of the cussing, but we'll talk about that. And then in regards to the spread, right now we're just going to say the numbers vary from 12.1 to 32.7. In the next section, we're going to calculate the standard deviation, the interquartile range, and the range to describe the spread. And so let's write this out. So there's so we will say, first of all, the center, you would say the assembly times. It is very important that you say in context. In other words, mention whatever is being talked about. So in context, always state the context. Once again, I grade these things every year, and these AP exams, and I can't tell you how many times a kid will do a beautiful job of cussing, but they leave out the context, and so they only get partially correct, and so that's sad. So the assembly times are centered. They are centered around, and I'm gonna say like 20 to 24 minutes. 20 to 24 minutes. Okay, so there you go. That would take care of the C. For the U, for the unusual values, there appears to be no outliers or unusual values. We call them outliers. Okay, and then in regards to the shape, all right. So these are the terms in regards that you need to say in regards to the shape, and so. Let me see here. All right, so I'll just. All right, so let me just go ahead and say what this is, and then I'll talk about it in a second. The shape of this is right skewed. It has a tail going to the right, and so the shape is right skewed. It is right skewed. Okay, right skewed, and then in regards to the spread, the times or the numbers, the times vary from 12.1 to 32.7 minutes. And there you go, that's cussing. Now let me go back in regards to, this is what you really need to say in regards to the shape. Here's some terms to use for shape. Terms that can be used for shape when you're describing the shape. Okay? First of all, it could be symmetric. And it doesn't have to be the exact mathematical definition of symmetric. Symmetric just means that it's roughly, it has a line of symmetry. And it can be a little bit off, but that's okay. But in general, you can draw a line like this, and it's the same on the left and on the right. It may be, and this one happens to be, it could be mound-shaped. Or bell-shaped, as we call it. In other words, it looks like just a little mound. It really has a high part, and it has, and then lower on the tails, as we call them. And this is what we call unimodal. This is what we call unimodal. So it just means it has one mode. Modes are places where it sticks up. Okay. Now it might be bimodal. Bimodal means it has two little mountains that are sticking up. So it could be like that, and it could be like that. Now technically, the mode is, the number that occurs most often, but to us, it's just a mode is any place that's sticking up. So this would be what we call bimodal. Or it could be left skewed. Now, left skewed means this. It means it has a tail going to the left. Tail to the left. And so left skewed means it looks like this. It's like that, has a tail going to the left. Okay? And of course, right skewed, as you may guess. So right skewed means it has a tail going to the right. So right skewed means it has a tail going to the right, Tail going to the right. And so that is going to be something that looks like that. Has a tail going to the right like that. So that wouldn't be heavily right skewed. I mean, heavily right skewed would be, something like that, and then it goes womp like that. That would be heavily right skewed. So that's typically what we see. Certainly, our data here, that's skewed to the right, has a tail going to the right. Now, and then another word, it could be uniform. Uniform just means it's going straight across. So uniform just means it looks like kind of a rectangle, pretty much just all the numbers are kind of occurring the same. Doesn't have to be exactly going straight across. It just means it's just kind of flat like that. No numbers are really occurring significantly more than any other numbers. And so when you talk about shape, you really need to say really one of these. If you said one of these in regards to shape, you should be fine. Okay, and so you have to look at it, and we'll look at different examples of different distributions, and your book certainly has a lot of different examples, and so, but it's really one of those words. Okay, and that's really being able to cuss. Like I said, that's kind of the heart of this section. Now, the other thing, really the last thing, is you have to compare two distributions. When you compare two distributions, in other words, two listed numbers, they don't give you just one list of numbers, they give you two lists of numbers, and you have to cuss using comparative phrases. So comparative phrases like greater than, less than, or roughly equal to. In other words, you're going to say the center of one is around this, which is greater than the center of this one, which is around this. And the spread of this one, is this, which is greater than the spread of this one, which is this. And so looking at an example, so let's say if we were looking at these test scores for tests that were given at Grissom and at Huntsville High, and let's say there's a histogram of Grissom's test scores, and there's our frequency table. Certainly looks mound-shaped and symmetrical. And there's Huntsville High's. Huntsville High's is very right-skewed. All right, and you were asked to compare these distributions. You immediately say to yourself, I'm going to cuss, and I'm going to use comparative phrases like greater than, less than, or roughly equal to. And really comparative phrases in regards to the center and the spread. In regards to the shape, you can just describe the shapes and just state whether or not there's outliers. And so this is what I would say in regards to that. The test scores, make sure, once again, please mention the context. The test scores for Grissom have a higher center, there's my comparative phrase, of about 75 to 80, whereas Huntsville's, which is around 65 to 70. So I've compared the centers using comparative phrase, thus I would get credit for center. Grissom has no outliers. Huntsville may have outliers from 95 to 100. Over here, those may be outliers. Like I said, we'll have a formula for that in the next section. All right, Grissom's shape is mound-shaped and symmetric, while Huntsville's shape is skewed to the right. Okay, and so in general for outliers and for shape, like I said, you don't have to have comparative phrases. And they both have a similar range, both varying from 50 to 100. We don't know the exact values here. We do know that Huntsville High has 15 numbers that are somewhere between 50 and 55. So when you look at a histogram, that's one of the disadvantages of a histogram is you can't tell what the exact numbers are. So like Grissom has 5 numbers between 50 and 55. We don't know what those numbers are. Okay, they could all 5 of them be 50, or they could all 5 of them be like 54. All right, so that's kind of the way histograms do that. So that's how you do comparative things. I want to show you how to do a stem and leaf plot, which is the last thing for section 1-2, and so the last thing for section 1-2, and all right. So this one says this: there are 2 locations of a restaurant in a city. One has a river and one is located downtown. At each location, the amount of money in hundreds of dollars earned on a number of randomly selected days is shown below. Create a back-to-back stem plot of this data and compare the distributions. And so first thing I want to do is just make a regular stem plot. So back-to-back stem plot means you're going to do it with 2 distributions or 2 lists of numbers. And I'm just going to do it, first of all, just with one of these lists. So first of all, I'm going to make a stem plot of the amounts of money, the money earned from the river location. And so this is what we're going to do. First of all, we have to label this. And so we'll say money earned. And so we'll say money earned. All right, and then so we say stem, and like that, and then we will say leaf. Okay, and all right, so the way you make a stem and leaf plot, the stems are going to be the numbers that are in this case on the left side. They're going to be your tens place here. Now realizing, make sure to pay attention to the units in these problems. This is in hundreds of dollars. And so this 28 here, that represents $2,800. So keep that in mind. That can be a little tricky thing. But for our purposes, we're just going to do this, okay? All right, and so for the stems, we'll use the tens place of these numbers. And now, by the way, if you had numbers that had more more than two things, like let's say if your numbers were like 512 and 642, you could round these. You could say, well, I'm going to use just 51 and 64, and like if you had 659 and 66, I'll use those values for my stem and leaf plot. But let's just go ahead and do this. And so the stems are my tens places, so they're going from 2 to 7. So 2, 3, 4, 5, 6, 7. All right, and then the leaves are going to be the ones place. So this 22, I'll put a 2 here, and that represents 22. And then 28, like that. It's very important that your digits take up the same amount of space. Like if you had a 31, like a couple of different 31s, you don't want to bunch them together like that. That wouldn't be good because it wouldn't show us the shape of the distribution properly. And so for my 30s, I have 35, I have 38, and then I have 44, 48, and 49. And then I've got 53 and 58, and I've got 61, 66, and 68, and then 72 and 79. And so there we go. And then we have to put a key. So our key tells us what the stem and the leaves represents. And in this case, it's in hundreds of dollars. So like this 72 represents $7,200. So 7/2 equals $7,200. And so the key communicates that this 22, the 2 goes in the thousandths place, and then this 2 goes in the hundredths place. So that would be $2,200. And so there we go. That's how you make a stem plot, otherwise known as a stem and leaf plot. And you can tell it's kind of like a histogram that's turned sideways, by the way. So if you turn it sideways, the histogram would look like that. And so that would, this is it's pretty uniform. It's going pretty straight across there. It's a really small data set, so, but anyway. Okay, now here's how you make a back-to-back stem and leaf plot. So this was with the river location. So that was with the river. And then over here, we're going to do it with the downtown. So over here, our leaves are going to be on the downtown locations, and we'll just go in the other direction. Okay, and so at the downtown location, we have a 37, so I put a 7 there. That represents 37. And then we have a 42, a 46, a 47, a 49, and a 49. Like that. And then in the 50s, we have 51, 52, 54, 54, and then 56, 58, and 59. So that'd certainly be a cluster of values. And then 60. There we go. And so there we go. There's our back-to-back stem plot. Of course, it's using the same key. And so now when you're asked to compare these two distributions, I think what stands out the most is that the river values are more spread out. They have more variability. These are more bunched together. They have less variability. But this is how I would do comparative cussing with this data set, and I just wrote it here. And so first of all, the centers. All right, I have to compare the centers, and so the money earned, there's the context, say the context every time, from the river location has a similar center, there's my comparative phrase, to the center of the downtown, both around 4,500. The river has more variability, okay, than the downtown, so more variability, that would be your comparative phrases. The river's value vary from 2,200 to 7,900, while the downtown's value vary from 3,700 to 6,000. The river's values have a uniform shape, while the downtowns have a roughly mound shape, and neither has any outliers. So I changed the order of my cussing there, but that's okay. And then lastly, something you may want to do, you may be asked to do, is do what is known as split the stems. And so I did this with the downtown data, because you notice when data is there, most of the data is just in 2 classes, and so it's really hard to make a judgment in regards to the shape. But if I split the stems, what that means is, like for the 30s, this 3 represents from 30 to 34, and that represents from 35 to 39. Each of them represents 5 numbers. And so I split the 40s in half. This represents all the 40s from 40 to 44. This represents all the 40s from 45 to 49, and so forth. This is the 50 to 54, 50, 55 to 59. It has to have the same number of numbers in each part. Okay, so you wouldn't be able to do it in thirds. You can't have like 40 to 42 and then 43 to or whatever, because you wouldn't have the same number of numbers in each stem. But you would be able to do it in 5s. You know, have this one represent 40 and 41, this one 41 and 42. But anyway, most of the time it's done like this. And so you'll notice, so this represents 42 and 44, and that's 46, 47, 49, 49. And that allows you, in this case, it allows you to more easily see that, yes, it is sort of a mound-shaped, symmetrical, pretty much, distribution. And that's it. That's it for section 1-2. If you have any questions, please send them to me. Do a good job on the problems, and I hope you just have a great day.